And welcome back for the last video for our series on the Chapter 6 practice test. We've got FRQ number 3 today, and 82% of cookies from ChipsMate contains 24 chocolate chips or more. A local elementary school looked at the number of chocolate chips in a random sample of 120 cookies. So there's a lot of numbers floating around here, but the thing to know is that the 24 chocolate chips is not really a number that matters to this problem. We just want to know a lot of chocolate chips or not as a lot of chocolate chips. So the first part here is to show that x, which is the number of cookies with a lot of chocolate chips, is a binomial random variable. And we know we have a binomial random variable if we satisfy every part of bins. B stands for binary. So do we have a binary outcome? Is it only two things that can happen? And in terms of the number of chocolate chips, yes. The numbers make it a little bit difficult, but either there's more than 24 chips in a cookie, or there's going to be 24 or less chips in a cookie. So binary works. I stands for independent, and basically this means that when I take one individual and I look at it, its state doesn't affect the state of the other of another chocolate chip cookie. So we're saying that the number of chips in one cookie does not affect the number of chips in another. Now that may or may not be true if you think about it, but we're actually going to just assume right now that the number of chips is binary, or whether or not one cookie has more than 24 chips doesn't really affect whether or not the next cookie or any other cookie has more than 24 chips. N stands for a set number of trials, or set number, and here we're looking at 120 cookies. So N equals 120. S stands for same probability, and yes, the same probability of success really is consistent throughout every chocolate chip cookie. We would write P is equal to 0.82. So since we satisfy all of bins, this x is a binomial variable. And we can shorthand writing this as x equals b for binomial, 120, 0.82. Next, we want to calculate and interpret the mean and standard deviation for x. Luckily, for a binomial random variable, there are formulas for the mean and the standard deviation. So the mean, that's just going to be equal to NP, which is 120 multiplied by 0.82, or just 98.4. The standard deviation is equal to the square root of NP 1 minus P, which is the square root of 120 times 0.82 multiplied by 0.18, or about 4.21. We're going to go about interpreting with our sentence frames again. And here's our sentence frame for the mean. So if many samples of 120 cookies are chosen at random. Now remember, since this is a binomial random variable, you have to put that 120 into your interpretation. So if many samples of 120 cookies are chosen at random, the average, and we're looking at the number of cookies with more than 24 chips, would be about 98.4. Now that we have our interpretation for the mean, let's get the sentence frame for standard deviation. So a random variable, what we're actually counting is the number of cookies with more than 24 chips. And that typically varies from the mean of, what was the mean? Oh, 98.4 by about, and the standard deviation now is 4.21. So 4.21 cookies. The number of cookies with more than 24 chips typically varies from the mean of 98.4 by about 4.21 cookies. And I did forget to put 120 here. So we better make sure we put down in a sample of 120. Don't forget that when you have a binomial random variable, you have to put the sample size, the number n, in your interpretations. Letter C. Can we use a normal distribution to approximate x? So two things have to happen here. We need to make sure that we satisfy the 10% rule and that we also satisfy the large counts condition. In other words, 120 must be less than 10% of the number of cookies produced by chipmates. And this kind of makes sense because that just means that chipsmate has to make more than 1,200 cookies, which seems pretty fair. Now for large counts, both NP has to be greater than or equal to 10 and N1 minus P has to be greater than or equal to 10. So let's calculate those. NP, that's equal to 120 multiplied by 0.82, and that's equal to 98.4. In other words, it's the mean of the binomial distribution. So this is definitely Now for n1 minus p, I actually do a little bit of cheating here because I don't multiply 120 multiplied by 0.18, although you certainly could. I like to just think of this as a complement of that 98.4. So if I subtract 120 from 98.4, I think I get 21.6, which is definitely greater than or equal to 10. So since both of these quantities are greater than or equal to 10, we've satisfied large counts. We satisfied 10% rule. We did large counts, so we can use a normal distribution. We can use a normal distribution for x, which put another way, we can say this. We knew that x was binomial with a number of trials 120 and a probability of success of 0.822. But it's also approximately equal to a normal distribution with a mean of 98.4 and a standard deviation of 4.21. So all three of those things, or the binomial, is about equal to the normal distribution. Okay, so for the thrilling conclusion, the school found only 90 cookies with more than 24 chips. Remember, we were expecting 98 cookies, and they found 90. Can we conclude that 82% of the chipsmate cookies contain more than 24 chips? And, well, basically, let's do this. What's the probability of finding a sample of 120 with 90 cookies or less? So if x is the number of cookies in a sample of 120 with 24 or more chips, what's the probability that x is less than 90? And we can use a normal distribution for this. Our z-score is going to be 90 minus 98.4 divided by 4.21. That gives us a z-score of -2. So our problem, the probability that the number of cookies with more than 24 chips is less than 90, that's equivalent to saying what's the probability on a z-curve that this z-score is less than -2. Over on my calculator, I can figure that out with a normal CDF. So we want to go less than -2. So we'll do the probability less than 1e99 to 2. And that gives me a probability of, oh, -2. My bad. Let's change that to a -2. And yeah, 0, 2, 2, 8. Good. So the probability of getting a 100 cookies with 90 or less chips, or 90 or less cookies with 24 or more chips, that's equal to 0.228. And the magic part here is that that is less than 5%. And remember what we said. When the hypothetical probability is less than 5%, we have results that are statistically significant. Maybe I should rephrase that. When the experimental probability is less than 5%, then we have statistically significant results. In other words, if that probability was actually 0.82, then our 120 cookies, we would only have a 2% probability of getting those exact 120 cookies, which is a very low probability. And since it's unlikely to have occurred, the only thing that could be wrong is that 82% number. 82 is likely to be incorrect. So it's unlikely that 82% of the cookies have 24 or more chips. And we can actually conclude that less than 82% of the cookies have 24 or more chips. So when you compute the probability with a hypothetical, p, in this case 0.82, then if that hypothetical probability that is less than 0.05, then we have significant results, which means that the probability we started off with, 82%, is probably not correct, statistically significant. So that's it for our Chapter 6 practice test. Good luck to you, and good luck. Have a great one. Have a good test. See you all next time.